Okay, so now in this lecture you'll finally understand Shor's algorithm for factoring integers. So remember what we did in the last lecture. We talked about this primitive called period finding. And so today we'll see how to use this primitive in order to factor integers. So remember what period finding does. You're given a function f from some domain, like the integers from 0 to m minus 1. It's a function from integers mod n to just some set. And this function has a property that it's periodic with period r, that f of x equal to f of x plus r. Your challenge is to find r. So we saw that this is a difficult task to do classically, but on the other hand, quantumly you can do this very efficiently. And the way you do this is you have a circuit which looks very much like the one we saw for Simon's algorithm. So you have a quantum Fourier transform mod m, followed by the circuit to compute f, followed by another quantum Fourier transform mod n, and then you measure, and the result of this measurement gives you allows you to reconstruct what r is. Okay, so again, remember how we said in the case of Simon's algorithm, the quantum circuit could be seen as a virtual double slit experiment. So in the case of period finding, this circuit can be seen as a virtual multiple slit experiment, because after you do this quantum Fourier transform, you're in a superposition over all the numbers a mod n, and then when you compute f, you get summation over a of a mod m followed by f of a mod m, right? So this was sum over all a from 0 to m minus 1 of, you have a out here and 0 out here, and then after you do the compute f, you'll get sum over all a equal to 0 to m minus 1, and this contains a, and this contains f of a. And so now when you measure this, you will see some value of, f of a, and then in the first register you'll have a superposition over a plus r, a plus 2r, and so on. So these are your multiple slits that you've carved, virtual slits. And then when you do a quantum Fourier transform, you get interference pattern, which tells you, because these slits are r apart, you get interference at some quantity related to r, and so using that you can reconstruct what r was, the period was. Okay, so now how do we use this to factor a number? So remember what the factoring problem is. You're given some number n, and you want to write it in the form, in its prime factors, p1 to the e1, p2 to the e2, pk to the ek. Right now, if n is if n was a 1000-digit number, then classically this is very hard to factor. Of course, the most naive algorithm would just try all prime factors until you find one. But then if n were, the hard cases where n was a product of two primes, p times q, and say that each of p and q is a 500-digit prime number. So now in this case, trial division was going to take way too long. It'll take 10 to the 500 possible factors, divisors to try, and that's just hopeless. Now the fastest algorithms we know classically are much better than this, but they still take exponential time. And so this is why the factoring problem is considered cryptographically hard, and that's the basis of the RSA crypto system. Okay, so for the purposes of this lecture, just to make things conceptually simple, I'm going to assume n is of this form. It's of the form p times q, where p and q are two odd primes. But of course, everything I say is going to be completely general, and so it's going to work for any n, any composite n. which is let's say any odd composite n. Okay, so generally, more generally, if the number of digits or the number of bits, the length of the number is little n, right? Then if little n is the number of bits that it takes to write out capital N, then capital N is about 2 to the little n. And our classical algorithm, the best classical algorithms take time which is exponential in square root of n. Okay. By contrast, a quantum algorithm for computing, for finding the factors of n is going to run. So this is our best classical algorithm, and by contrast, our quantum algorithm for computing, for finding the prime factorization of n will run in time which is polynomial, say order n cubed, although we can improve it. The exponent might be squared, or using certain tricks we can improve it even further. But the most important thing here is that it goes from exponential time to polynomial time. So now, in order to understand how this algorithm works, we are going to have to understand some, we are going to have to understand some very elementary number theoretic facts, which I'll now explain to you. But to understand these simple facts, you'll of course need some background in what's called modular arithmetic. I hope you already have this background. If not, let me point you to some resources online that will help you understand that. So what's modular arithmetic? We say that two numbers a and b are congruent mod n if a minus b is divisible by n. So think of modular arithmetic as what happens when you have numbers around a clock face. So there you are counting modulo 12. So for example, if the time is 15 o'clock, well, you don't ever think about 15 o'clock, you subtract off 12 and you get a number always between 0 and, well, okay, so if you're really doing it mod 12, then you call 12 0, so your numbers are always 0, 1, 2, 3 up to 11. Okay, now if you don't already know about modular arithmetic, let me refer you to an online resource. There's a book on algorithms that I've posted on my web page. This is an almost final copy. This was the pre-copy edited version of the book, and the first chapter is on modular arithmetic. The second half of the second chapter is on the fast Fourier transform. And chapter 10 is on quantum factoring, so you have this resource available if you need to look up any of the background for modular arithmetic or some of these later topics. Okay, so now, assuming everybody knows about modular arithmetic, let's just go ahead and say let's work with an example. Let's say that we have n equal to 21. This is the number that we are trying to factor, and we are pretending that n is very large. 21 is too large for us to deal with by any of our standard methods, so what are we going to do? Well, it turns out that, okay, so normally, if you were looking at the square root of 1, in regular arithmetic, this would be plus or minus 1. And of course, indeed, that's also true mod n. So for example, you have 1 squared is congruent to 1 mod 21, and minus 1, which is also 20. When you square it, you'll also get 1 mod 21. Okay. So you know, minus 1 is the same thing as 20 mod 21, and if you go ahead and square 20, you will get 400, and you should check that 400 is congruent to 1 mod 21. Of course, you don't need to do this because you know 20 is minus 1, but okay. Now it turns out that mod n, when n is a composite, these are not the only two numbers that square to 1 mod n. So there's another square root of 21, and that happens to be 8, because 8 squared, which is 64. Now you can see when you reduce it mod 21, 21 times 3 is 63, and so the remainder is 1. So 8 squared is 64, which is 1 mod 21. Okay, so I claim that once you locate such a non-trivial, we'll call this a non-trivial square root of 1 mod 21. Once you have such a non-trivial square root, you can use it to factor 21, because now what we can claim is that the GCD of 8 plus 1 and 21, the greatest common divisor, is going to give you a non-trivial square root, and the GCD of 8 minus 1 and 21 will also give you a non-trivial square root of non-trivial factor of 21. Okay, so what's the greatest common divisor of 8 plus 1, which is 9, and 21? Well, the greatest common divisor of these two numbers is 3, which is indeed one of the factors of 21. And this number is 7, and the GCD of 7 and 21 is 7. So we managed to factorize 21 just by computing this non-trivial square root of 1 mod 21. Now, of course, there should be another non-trivial square root, because they come in pairs, and that would be minus 8. Minus 8 is the same as, well, what's minus 8 mod 21? It's minus 8 plus 21, which is 13. So I claim minus 8 squared, which is 13 squared, is also congruent to 1 mod 21. That's 169, and you should check that 168 is divisible by 21. And so you could have done the same thing with 13. You could have said GCD of 13 plus 1 and 21 is going to be non-trivial. So this was 14. And indeed, the GCD is, the greatest common divisor is 7. Also, the GCD of 13 minus 1 and 21. Well, what's this? This is 12. The GCD is 3. Okay, so you recover the factors of n. Okay, so what's going on here? Well, what's going on here is this general principle. If x is a non-trivial square root of 1 mod n, then the GCD of x plus 1 in n and the GCD of x minus 1 in n give you non-trivial factors of n. How do you prove this? Well, let's see. X is a non-trivial square root of 1 mod n, meaning x is not congruent to plus or minus 1 mod n. But it's a square root of 1 mod n, so meaning x squared is congruent to 1 mod n. What's another way of saying this? Meaning x squared minus 1 is congruent to 0 mod n, which means that n divides x squared minus 1. Okay, but then n divides x plus 1 times x minus 1. Okay, but what do we do with this? Well, remember, also x is not congruent to plus or minus 1 mod n, which is the same thing as saying, by the same kind of reasoning, that n does not divide x plus or minus 1. Okay, so now n divides x plus 1 times x minus 1, but n does not divide x plus 1 and n does not divide x minus 1. So how could it be? How could it be that n divides this product but it doesn't divide either one? Okay. Well, the only way it could be is if some of the prime factors of n divide x plus 1 and some of them divide x minus 1. So now what this tells us is that the greatest common divisor of x plus 1 and n must be a part of n, but in our case n is just a product of two primes, so this must give us one of the prime factors, and the greatest common divisor of x minus 1 and n must give us the other prime factor. Right? So for example, this might give us p, this might give us q, and that's how we can factor.